Okay, so we are looking at today math prep for physics. We're moving on from our unit on scientific ethics and scientific literacy in order to look at the mathematics that are prerequisite for a course in physics. So specifically what we're going to be looking at, and these are encapsulated in our check for prior knowledge questions, is how to work with numbers in terms of scientific notation, okay? How to do unit conversions, and how to solve basic math equations, algebraic equations, all of which are standard prerequisites for any successful course in physics. So let's get to it. And then here's our title slide right here. All right, so what we're up to today: learning the units of measurement used in physics and how to convert between units, learning how to use scientific notation to express extremely large or small numbers, and establishing the basics of equation solving needed for this course. So let's take a look at scientific notation. Scientific notation is very useful for taking very, very large numbers or very, very, very small numbers that would otherwise be very tedious or cumbersome to work with and converting them to a form that is much more manageable to work with, okay? So let's say we have 534.3, okay? 534.3, okay? So any number can be expressed in the form m times 10 to the nth, where m is called the mantissa and n is called the order of magnitude, okay? For writing in scientific notation, we proceed as follows, okay? If, for example, we're working with 534.3, we're going to start at the decimal point and move the decimal point to the left until you are between the first and second digit. In this case, what would be 5 and 3? We count the number of spaces you have moved. This represents the order of magnitude, okay? In this case, the order of magnitude is 2. If we move 534.3, we move the decimal point to the 5 and 3, we're going to move 2 spots. So as a result, the number of spaces we moved is 2, and thus our order of magnitude is 2. The resulting number we get after moving the decimal point, which in this case would be 5.343, becomes our mantissa. So as a result, 534.3 in scientific notation would be 5.343, the number we attain after moving our decimal point, times 10 to the second power, where 2 is our order of magnitude. So this works for any number where the number is larger than 1. So let's now take a look at a case where a number is greater than 0 but less than 1, such as 0.00000023, or 0.60's Michael Jordan, for those of y'all who are basketball fans. Okay? So if your number is less than 1 but greater than 0, here's the strategy we're going to follow. We're going to start the decimal point and move the decimal point to the right until you are between the first non-zero digit and the second non-zero digit. In this case, what would be 2 and 3. So move it all the way over all the spaces until it's between 2 and 3. Count the number of spaces you have moved, except this time the order of magnitude will be negative. So in this case, I'm going to move my decimal point 1, 2, 3, 4, 5, 6, 7 spots to the right. However, because we're expressing a number less than 1, our order of magnitude is going to be negative. There's a whole reasoning based on exponent rules and fractions that could be used to explain this, but here we're looking at just what we need for face value. So at the end of the day, if your number is less than 1, your order of magnitude is going to be a negative number. Okay? Take that at face value. The resulting number we attain after moving our decimal place is going to form our mantissa, so 2.3 will be our mantissa in this case, and the order of magnitude will be negative 7, so we can use that to write our number in scientific notation. 0.00000023 equals 2.3 times 10 to the negative 7th. So multiplication, m times, let's say we have two numbers in scientific notation form, m times 10 to the a, and n times 10 to the b. If we multiply these two numbers together, the resulting product is going to be the two mantissas multiplied together, so m times n, multiplied by 10, where the order of magnitude is going to be the sum of a and b. This is useful for extremely large numbers where multiplying extremely large numbers together is otherwise impractical. Doing it in this way with scientific notation allows us to conveniently evaluate the product without having to expand the numbers into an impractical and inconvenient form. Likewise, for division, if we are dividing two numbers are in scientific notation, again, m times 10 to the a, and we're dividing it by n times 10 to the b, the result is going to be m divided by n I have it as m times n right here because I forgot the slash, so there's a typo there, times 10 to the a minus b. So in this case, when we divide now, we're going to subtract the order of magnitude in our denominator from the order of magnitude in our numerator. So here's a quick check for understanding. You can pause the video and work this out if you like. If not, if you would like to see me work it out, that's what I'm getting ready to do. So write 0.000000563 in scientific notation. Okay? So in this case right here, we're going to move our decimal to the right until it's between the first two non-zero digits, which in this case would be 5 and 6. So we're going to have 1, 2, 3, 4, 5, 6 places moved to the right. And as a result of moving that decimal point, our number after we move the decimal point is going to be 5.63, so that's going to be our mantissa. While order of magnitude is going to be -6 since we moved 6 spots to the right. So our number in scientific notation would be 5.63 times 10 to the -6th. Okay? Now if we evaluate the following, let's say we want to evaluate the following, 3.2 times 10 to the -3rd and 2.0 times 10 to the 5th. Okay? How I proceed to do this is I would take 3.2 and multiply it by 2.0. Again, with the mantissas, we multiply the mantissas together, so we're going to get 3.2 times 2.0. And then we're going to multiply that by 10 to the sum of -3 and 5. Again, we add -3 and 5 together, so that's going to give us 10 to the -3 plus 5, or 10 to the second. 6.4 times 10 to the second is going to be our resulting number. So now let's look at unit conversions, okay? So there are three main prefixes that we need to know in physics in terms of unit conversions. The rest, such as nanometer, picometer, decimeter, all that stuff, they are used, but they're used less frequently. And we're going to focus on practicality here. So in terms of practicality, the three most used in physics are kilo, centi, and milli, okay? So kilo, represented by letter K, means you have 1,000 of whatever your base unit is. So if my base unit, say for distance, is a meter, which that's what we use to measure distance in physics, is meters instead of feet, a kilometer or kilometer is going to be 1,000 meters, okay? A centi represented by letter C, is going to be 1/100th or 0.01 of your base unit. So if my base unit is a meter, a centimeter is 1/100th of a meter. The best way to think about that is that a ruler, okay, a meter stick is a meter long and consists of 100 centimeters. So as a result, 1 centimeter makes up 1/100th of a meter stick, or 1/100th of a meter, hence the 0.01. And lastly, a millimeter, or a milli, all right, to reference the Lil Wayne song, a milli, a milli, a milli, is represented by the letter M, okay? And a milli represents 1/1000th of something. The idea being is that if you look at a meter stick, all the individual dashes are millimeters. And there are 1,000 dashes on a meter stick, so there are 1,000 millimeters in a meter. Thus, a millimeter makes up 1/1000th, or 0.001 of a meter. So now let's say we want to convert, okay, 34 let's say we want to convert from 1 meter to, or excuse me, from one unit to another unit here. So let's say we want to convert 34.6 centimeters to kilometers, which is overkill because that's 34.6 centimeters is a lot more eloquently written than whatever the unit is in kilometers, whatever measurement is kilometers. But it's for sake of explanations, okay? So we're going to start at the beginning unit. The first thing we're always going to do is we're going to start by the beginning unit and multiply it by its conversion to the base unit. So if we have 34.6 centimeters, okay, we're going to convert to our base unit, okay? So we want to get rid of centimeters, which means we're going to have centimeters in our denominator, okay? The centimeters are going to cross out. The unit that we're trying to end up with, the base unit, is what's going to be in the numerator. So we're going to have a meter unit in the numerator, okay? So now we have to identify the proper conversion from centimeters to meters. In that case, we can either write down that there's 0.01 meters, or excuse me, I actually have this in reverse, I believe. Oh no, I have this correct. You can either write down that there is 0.01 meters in a centimeter, aka that a centimeter is 1/100th of a meter, or you can multiply Or you can divide by 100 right here by noting that there is 100 centimeters in a meter. So you can either multiply by 0.01 or divide by 100, both of which are equivalent. So as a result, the centimeters are going to cross out, and you're going to have 34.6 times 0.01, which gives you 0.346 meters. So now the second thing that we're going to do, all right, again, we take note that the units are going to cancel out. So we're going to always be left the unit that we want in the numerator, and then we're going to cross out the unit that we don't want in the denominator. So we're going to repeat this process until we attain our desired unit. Specifically, we're going to convert from our base unit, which is meters, to our desired unit, which in this case is kilometers. Okay, so 0.346 meters. Again, we want to get rid of the meters, which tells us we need to have meters in the denominator, and we want kilometers, which tells us we're going to need kilometers in the numerator. Okay. And now we need to think about the conversion from kilometers to meters. All right, specifically we know there are 1,000 meters in a kilometer, so we're going to have 0.346 divided by 1,000, which leaves you with 0.000346 kilometers, or 3.46 times 10⁻⁴ kilometers. Please note, you do not have to do this step by step, but rather can do this all at once in one big cancellation. Okay, so we could have done 34.6 centimeters times 0.01 meters, crossed out the centimeters, and then multiplied that by 1 kilometer per 1,000 meters to cross out the meters and leave us with our answer in kilometers. Okay, so again, we're always going to convert to our base unit first. We're going to cancel out the units that we don't want, and then we're going to convert from our base unit to our desired unit. In this case, which in this case is kilometers. So a quick check for understanding, convert 36 centimeters to kilometers, or 36 meters to centimeters. What we take note of right here is first we want to convert to our base unit. Well, our base unit for distance is meters, so we've already completed that first step. So now we need to convert our base unit to centimeters. Okay? So we're going to have 36 meters, all right, times 100 centimeters per meter. Again, we want to cancel out the meters, so the meter is going to be a denominator. Centimeters is what we want, so centimeters will be a numerator, and now we need the conversion ratio between centimeters and meters, which is 100 centimeters per meter. So we're going to have 36 times 100, which equals 3,600 centimeters. Lastly, we would focus on equation solving, okay? So the key to equation solving is that we're going to apply the opposite operation to the equation until you get your variable by itself. So the way that I prefer to do this in terms of hierarchy of operations is actually to run in reverse of PEMDAS, okay? PEMDAS is used to simplify expressions, whereas the reverse can be used to isolate expressions. All right, so what I like to do is first focus on, are there any numbers that are added or subtracted? If so, I perform the inverse operation, which is subtraction and addition. So for example, if I have y minus 2 equals 0, I'm going to add 2 to both sides to get y equals 2. Next, I'm going to see if there's anything I can multiply or divide. If there are, I'm going to perform the opposite operation, which is division and multiplication, which is going to give me 5y equals 10. All right, so for example, let's say I'm looking at 5y equals 10 right here, okay? We're going to divide both sides by 5, which is going to give us y equals 2. We're going to get y equals 10 divided by 5, or y equals 2. And lastly, the last thing I'd like to check for is squared powers. All right, if I have a square power, like let's say y squared, we're going to take the square root, which is the inverse of the square operation. All right, so if I have y squared equals 4, I'm going to take the square root of both sides, which is going to give me y equals 2. For those of y'all who may be more sticklers, and trust me, I'm a stickler in this regard too, you may notice, wait, there needs to be a plus or minus sign on the 2. Indeed, when we're doing mathematics and we take the square root of a number, square root of both sides of an equation, we need to have a plus or minus sign attached to our solution, as plus or minus 2 squared will give you 4. However, in physics, we do not account for a negative sign because the negative sign tends to give us unreal solutions, meaning solutions that don't make sense. So for example, if instead of y squared equals 4 here, I had t squared equals 4, taking the square root of both sides would give me t equals plus or minus 2. T in physics often represents time. Now the problem with t equals plus or minus 2 is that t equals minus 2 would imply we're actually moving backwards in time. A minus 2 value means we're moving backwards in time by, say, 2 seconds. So as a result, that doesn't make sense because we can't move backwards in time. So in physics, we forget about the negative and we keep strictly the positive root of our square root. So let's look at some examples in practice. Solve for x in the equation at right. 3x squared plus 5 equals 32. I take note of the fact that 3x squared plus 5 equals 32 has a 5 added on. So first thing I'm going to do is I'm going to subtract 5 from both sides, which is going to leave me with 3x squared equals 27. The next thing I'm going to do is after I calculate out 3x squared equals 27, I'm going to divide both sides by 3, since I have 3 multiplying the x squared. And what that's going to leave me with as a result is x squared equals 9. So now in my last step, I have x squared equals 9. I need to get rid of the x squared. I need to get x by itself, which means I'm going to take the square root of both sides, and that's going to give me x equals the square root of 9, or x equals 3. Now let's look at another example here, and again, you can pause the video if you would like to test yourself. We have 8 minus 2/3 y equals 4, okay? So what specifically is happening here? We're going to have 8 minus 2/3 y equals 4. First thing we take note of is that we have 8 added on, so we're going to subtract 8 from both sides, which gives us minus 4, okay? So as a result, we're going to have negative 2/3 y equals negative 4. So next thing that we're going to do here is we have a negative 2/3 multiplying our y here. So what do we do in this case? Do we divide by 2, negative 2? Do we multiply by 3? Which one do we do? It actually turns out we do both, and in the result, what we actually end up doing is we're going to multiply our equation, both sides of our equation, by the reciprocal. So whenever you have a fraction multiplying your variable, you're always going to multiply both sides by the reciprocal of that fraction. So if we have negative 2/3 y equals negative 4, we're going to multiply both sides by negative 3 over 2. That's going to yield for us that y equals negative 4 times negative 3 over 2, or y equals 12 over 2, which gives us y equals 6. And these are the basic mathematics that we'll need for our physics course moving forward.